All right, yesterday you looked at formulas of binary ionic compounds and wrote their names. And the name is the name of the cation and the name of the anion. Ignore any numbers in the formula. There's a rhythm to them. Sodium oxide, potassium sulfide, magnesium chloride. I hope you noticed the cations were always found on the left side of the periodic table. Over here. And the anions were always found on the right in the nonmetals. I hope you also noticed that you were using these "ide" endings over and over again. We will be including ions with other endings. You wrote them in your chart, and you need to recognize from the "ide" ending when you have a simple nonmetal anion and when you have a different ending, which means you have something else. Okay, let's look at answers from number 2 yesterday. So the first one, Na3N. If we look at the periodic table, we look on the left for Na because we know that's a metal. Pretty small in this, but I hope you can see it. Sodium. N, we expect it to be a nonmetal. It's going to be over here somewhere. There it is. N. Nitrogen. And we have to change the ending on the nonmetal ions to "ide." So it's going to be nitride. So that compound is going to be sodium nitride. We don't do anything with the 3. The cation, the positive ion, is sodium. The anion, the negative ion, is nitride. We just name the 2 ions, sodium nitride. Second one, K and O. We're going to look for K on the left because we know it's a metal. We're going to look for O on the right. We know it's a nonmetal. Oops. Go back. K, potassium. O, oxygen. We're going to change that ending to "ide" and make it oxide. So that formula is going to be potassium oxide. Next one's a little tricky. Ag is in the transition metals. You might have hunted around until you found it in the middle of the periodic table. You might have looked at your table of ions and seen that it is in there. Ag is silver. Br in your nonmetals, bromine. The ion is bromide, so we have silver bromide. Mgi2, we ignore the 2, of course. Mg is in the metals. You find that's magnesium. I is the symbol for iodine, and when we have the negative ion, we call it iodide, so magnesium iodide. And this last one, Sr, is on the left. It's down pretty low. It's not one that we've used a whole lot, but that is strontium. And oxygen, for the nonmetal, we change that to oxide, so we have strontium oxide. All right, let's consider a formula. What does the name? What does the name tell us? It tells us the 2 ions. We know that. Positive first, then negative. What doesn't it tell us? Something pretty obvious it doesn't tell us. It doesn't tell us how many of each ion are in the formula. That's what we have to figure out. Why, you are asking, don't they just tell us? Because there is one and only one way for any pair of ions to combine to make a compound. That's right, for any combination you can think of, positive and negative, there's only one ratio that works, because that's what the formula is, right? A ratio. There's only one ratio of positive and negative ions that is neutral overall, and it has to be neutral, remember? Full of positive and negative charge, but they exactly balance, making the compound neutral overall. Okay, so we're going to use the requirement that the crystal be neutral overall. Remember, these things always make crystals. That means the formula is neutral because the formula is the simplest ratio of positive and negative ions in the crystal. Here's the thing. For any combination of positive and negative charge, there's only one formula that makes it neutral. Let's look at one example. Calcium bromide. I guess we need to start with the charges on the ions because we want to use the ion charges to figure out what formula makes it neutral. Calcium, over here, group 2, ion charge of 2+. comes back. Calcium, 2 plus. Bromide. That's bromine over here on the right. Charge of -1. Had to write them on different lines because of the limitations of the animation. Now, if we had equal numbers of calcium and bromide ions, we'd have 2 times as much positive charge as we had negative charge in our crystal. That's no good. But if we had twice as many bromides, the negative charge in our formula would be 2 times -1, which is -2, which would exactly balance the +2 from the calcium. So calcium bromide has to have twice as many bromides as it has calcium. That is twice as many Br- as it has Ca2+, and the total charge is then 0. We write the formula CaBr2, 2 times as many bromides as calciums. All right, another example. Potassium sulfide. Once again, we go to the periodic table. You have written the charges above the columns. Potassium is somewhere over in the metals. There it is. Maybe by now you know that that's K, and that's got a +1 over it. Sulfide, we've got to go over to the nonmetals. We find sulfur. Sulfide is the changed ending for sulfur, and above that is 2-. So we have potassium 1+ and sulfide 2-. All right. Once again, these do not match, right? We have 2- but only 1+. We have twice as much negative charge as positive charge. We need 2 times as many. Let's go back. We need 2 times as many potassiums. 2 times +1 will be +2, +2, and that will balance the -2, and we'll get 2 potassiums to 1 sulfur, K2S. Strontium oxide, another one. Okay, here's that Sr again. We're looking in the metals. It's down low on the left. Sr, strontium, takes a charge of 2+. Oxide, that's our oxygen, 2-. So we've got strontium oxide has Sr2+ and O2-. All right, +2 - 2, those are equal. So we expect those to combine in a 1-to-1 ratio. And we get SrO, strontium oxide. Jumped ahead there. Aluminum oxide. This one is a little bit trickier. Okay, aluminum, remember, is really weird. It's right there. In fact, it's the only metal that touches the stair steps. We always tell you that those are metalloids, but you know aluminum is a metal. They make aluminum cans out of it. It's shiny. It conducts electricity. It does everything like a metal. It's way over here by itself, and that 3+ applies to aluminum. So aluminum is 3+. Oxygen, again, I'll put too many examples with oxygen, is over here. Oxide is oxygen, 2-. So we have Al3+ and O2-. Now, this one is a little more challenging than the ones we've done before because 3 doesn't go into 2 and 2 doesn't go into 3. So we can't just take 2 of one of them or even 3 of one of them and make it work. So how do you take these 2 different numbers that really don't mesh very well and make them work? Well, the total charge is going to have to be some number that 2 goes into and some number that 3 goes into, because the positive charge is going to be made up of some whole number of aluminums and the negative charge is going to be made up of some whole number of oxygens. And you may or may not recognize this, but this is the conditions for needing a least common denominator. We need to find a number that both 3 and 2 go into. We call that the least common denominator, and that would be the product of 3 and 2. 3 times 2 is 6. Let's think about that. 2 goes into 6. If we had 3 oxygens, we'd have 3 times 2-. We'd have a total negative charge of 6-. If we had 2 aluminums, we'd have 2 times 3. We'd have a total positive charge of 6+. 6+ and 6-. 3 plus 3 is 6. 2 plus 2 plus 2, or negative 2 plus minus 2 minus 2 is negative 6. So aluminum oxide has 2 aluminums in it and 3 oxygens. Al2O3 aluminum oxide. There's another kind of quick and dirty way to do that. We do take the charges and we crisscross them. We ended up multiplying by 3 and dividing by 2, multiplying by 2 and dividing by 3. We ended up, when we made that formula, with the 2, no plus or minus on the aluminum, and the 3, no plus or minus on the oxygen. So if you have trouble, I really would like everybody to understand how to do it the other way, but if you have trouble, you're stressed out, you're on a test, you can always try to do the crisscross. So I hope that is enough for you to go ahead and do sections 3 and 4 of the worksheet, writing formulas from the names.